All right, let's talk about the fundamental building blocks of, well, everything. Atoms. And by the time we're done here, you're going to understand the simple rules for building pretty much any element from the ground up. So, let's dive right in.
Okay, to really wrap our heads around this, let's try a little thought experiment. I want you to picture a giant football stadium. Got it? Now, imagine we could somehow inflate a single atom to fill that entire stadium. How big do you think its nucleus, its very center, would be?
Believe it or not, it'd be the size of a single blueberry. That's it, a blueberry. The entire rest of that stadium, that's just the vast empty space where a few tiny electrons are zipping around. And that right there is the first kind of mind-blowing thing you have to understand about atoms. They are almost entirely empty. So here's what we're going to cover. We'll look inside that empty atom, figure out what gives an element its unique identity, and then see what happens when we play around with its parts to make isotopes and ions. And finally, we'll tackle why those atomic weights on the periodic table are never nice round numbers.
All right, first up, let's zoom way in on that blueberry nucleus and the space around it and meet the three fundamental particles that make up every atom.
Okay, so every atom has three key players. You've got your positive protons, your neutral neutrons, and your negative electrons. Now check out that mass column. Protons and neutrons, they both weigh about 1 atomic mass unit, or AMU. But the electron? Whoa, it is tiny, almost 2,000 times lighter. It's so light, it's practically weightless compared to the other two. And this brings us right back to our football stadium. All the mass, all the actual stuff of the atom is crammed into that tiny little blueberry at the center. But it's those super light electrons that get to have all the fun, taking up basically all the volume of the entire stadium. It's this incredible split between where the weight is and where the space is.
So you've got these three particles. How do we know if we're looking at an atom of gold or an atom of helium? Well, it turns out there's one incredibly simple rule that defines everything. And this is it. It's called the atomic number, which we label with a Z. And it's just the count of protons in the nucleus. That's it. This isn't just some random stat. It is the atom's social security number, its fingerprint. It is the single most important number that defines an element.
So let me be super clear about this. If an atom has 6 protons, it is always carbon. End of story. I don't care how many neutrons it has. I don't care how many electrons it has. 6 protons is carbon. If it has 8 protons, it's oxygen. This is the one rule you cannot break.
Okay, so what about the weight? For that, we look at the mass number, or A. And this is super easy. It's just the total number of heavy things in the nucleus. So you just add up the protons and the neutrons. That's your mass number. All right, so if the number of protons is locked in, what happens if we mess around with the number of neutrons?
Well, that's how you get what we call isotopes. You can think of isotopes as siblings. They're all part of the same element family, they all have the same number of protons, but they weigh a little different because they have a different number of neutrons. Magnesium is a great example. See, every magnesium atom, no matter what, has 12 protons. That's its identity. But you can find magnesium atoms with 12 neutrons. We call that magnesium-24. Or you can find them with 13 neutrons, that's magnesium-25. And yeah, even some with 14 neutrons, or magnesium-26. They're all still magnesium, just slightly heavier or lighter version. Okay, so changing neutrons gives us isotopes. What about those other particles, the really lightweight electrons? What happens if we change their number? When you do that, you create an ion. See, in a normal neutral atom, the number of positive protons is perfectly balanced by the number of negative electrons. The charges cancel out. But as soon as you mess with that balance, the whole atom gets an electrical charge. And there are 2 ways this can go. If an atom gains an electron, it suddenly has more negative charge than positive, and we call that a negative ion, or an anion. But if it loses an electron, now the positive protons are in the majority, and it becomes a positive ion, or a cation. Simple as that. All right, this next part solves a mystery that confuses a lot of people. We just said the mass number is a whole number, right? You're just counting particles. So why, when you look at a periodic table, are all the atomic masses these weird decimals? And the reason is pretty cool, actually. That number you see on the periodic table, it isn't the weight of any one single atom. It's actually a weighted average of all the different isotopes of that element, based on how common they are out in the real world. But let's use boron to see how it works. Out in nature, you find 2 types of boron, a lighter boron 10 and a much more common, heavier boron 11. So what we do is take the exact mass of boron-10 and multiply it by how common it is. Then we do the same thing for boron-11, add those two numbers together, and voila, you get the weighted average, 10.81.
And here's the really important takeaway. There isn't a single boron atom anywhere that actually weighs 10.81 AMU. It doesn't exist. An atom is either boron-10 or boron-11. That number on the chart is just the statistical average. Like saying the average family has 2.5 kids. It's a useful number, but it doesn't represent any single atom.
Okay, so let's recap the big rules. Number 1, protons define the element. That's the one thing you can't change. Number 2, changing the neutrons gives you different isotopes. Same element, different weight. Number 3, changing electrons gives you ions. Same element, different charge. And that decimal on the periodic table? Just the average weight of all those isotopes combined.
But before we go, there's one last little mystery, a real head-scratcher. If you take the parts of a carbon atom, 6 protons, 6 neutrons, and 6 electrons, and weigh them all separately, and then you weigh a fully assembled carbon atom, the parts actually weigh more than the finished product. Some mass just vanishes. They call this the mass defect. And that leaves us with a huge question. If particles weigh more apart than they do when they're fused together inside a nucleus, where does that missing mass go? The answer, it turns out, is tied to the immense energy that binds that nucleus together, an idea that literally changed the course of human history. Something to think about. Thanks for joining me.